So friends, today we will discuss about dissociation of acids. So today we will discuss about dissociation of acids. Okay. So consider the dissociation of a weak monobasic acid like HA in water. So it is a weak acid, so it will not completely dissociate and it will form H3O positive plus A negative. Okay. So now Kc. Okay. So you know this Kc equilibrium constant. So now we'll do, since the water is present in large excess in dilute solution, its concentration may be taken as a constant. Okay, this water. So this H3O positive simply indicates that hydrogen ion is hydrated, so it may be represented as H positive. Okay, so this equation can be written as Kc equals to H positive. Since it simply indicates the hydrogen ion is hydrated, it may be represented by this, and it will remain same and this H2O it present in a large extent, so it's also a constant. Let's assume it is K. So now if we multiply two constant, it will form another constant, so it will be Ka, because we are discussing dissociation of acids. So it will be Ka equals to H positive into N negative divided by Ha. Okay, this Ka is represented by dissociation constant of acid. Okay, this Ka is called dissociation constant of acid. Now let us consider an example of acetic acid. If it will dissociate, it will form H positive and CH3COO negative. So first, direct it will not dissociate. First it has original concentration. Okay, original concentration, it will be C. Let us assume that the concentration is C. Then at the initial state it will not form any ions. So at equilibrium concentration, okay, this C will dissolve this much and it will form what? C alpha and C alpha. Okay, so now dissociation constant K equals to H positive, you know, earlier I have teached, CH3COO negative divided by CH3COOH. So this we can write in terms of these three. Okay, so it will what? H positive, it is C alpha into this COOH, it will be C alpha divided by this C1 minus alpha. Okay, now it will be C square alpha square divided by C1 minus alpha. Okay, now it will cancel C alpha. Now alpha is very small. Okay, alpha is very small, so 1 minus alpha in the denominator may be taken as 1. Okay,
Alpha is a very small, so 1 minus alpha is nearly equals to 1. Okay, now the equation will become K equals to C alpha square. This denominator will become 1. So this can be written as alpha equals to root over K by C. Okay, and this equation is called Oswald's equation. Okay, so what is Oswald's versus Oswald's dilution law? Okay, state Oswald's dilution law. Okay, so the answer will be, for a weak binary electrolyte with small degree of ionization, small degree of ionization. Okay, the degree of ionization is inversely proportional is inversely proportional to the this what is this degree of ionization is inversely proportional to the square root of the initial concentration okay, of the electrolyte. So for a weak binary electrolyte with small degree of ionization, the degree of ionization is inversely proportional to the square root of the initial concentration of the electrolyte. You can understand through this. This is the degree of ionization for weak electrolyte, okay, and it is inversely proportional to the square root of the initial concentration of this electrolyte. Okay, so now this equation can be written as, we know that what this C, the concentration C is expressed in mole per liter. Okay, this is expressed in mole per liter. Okay, so therefore the volume V of the solution of containing 1 mole of the electrolyte will be 1 by C. Okay, 1 by C equals to V. So putting 1 by C equals to V, our equation will become this equation 1. Then 1 becomes, what it will become, root over KV. Okay, so we can write another Oswald's law of dilution for a weak binary electrolyte with small degree of ionization. The degree of ionization is, this time it is directly proportional. It is directly proportional to the square root of the volume. Okay, square root of the volume, volume containing 1 mole of the electrolyte. Okay, and this volume will be in liters. Okay, so this is Oswald's dilution law. Okay, thank you.